Good day, I'm Maile Matsiba. Welcome back to our channel. Today we are beginning with our CIR 211 lessons. CIR 211 is the second chemical engineering module at the University of Pretoria. We are looking at example 2.3.1.1. It says methane gas CH4 is burned fully with 10% excess air. Assume the air is 40% saturated with water vapor. The air temperature is 30 degrees Celsius. The atmospheric pressure is 90 kilopascals. Show by calculation that if 1 kilomole of methane is burned, the exhaust gas will be 2.2 kilomole H2O, 1 kilomole CO2, 0.2 kilomole O2, and 8.28 kilomole N2. So that is basically the problem statement. So they are saying that given the information that we are given, if 1 kilomole of methane is burned fully, prove through calculation that the exhaust gas will have this analysis. So before I actually decided to already drew the sketch here. So we have our methane in 1 kilomole, and then we have our air that is actually being charged in the combustion chamber, and then we have the exhaust gas there. And it's also important, like the problem statement has highlighted, that the air is 40% saturated with water vapor. So just a little bit of a highlight as we start this. In this very first video, I'm gonna do lots of explanation, especially concepts that we're gonna be carrying them through this module. So I hope it won't be too long, this video, but I'll try by all means that it doesn't really become so long. But in the same way, equally, I'm gonna make sure that I actually highlight the blind spots that I believe they are very, very much important, and they will serve as a very strong or solid foundation as we're gonna be moving on throughout this module. So for us to solve that, the first thing that we need to do is to actually just write down our reaction equation. We have our methane plus O2, which we know conventionally or traditionally, it gives us CO2 plus H2O. We always know that a hydrocarbon, when it combusts, it actually gives us CO2 and H2O. Now, if you balance it, it's gonna be 2 here, and we're gonna have 2 here. So that's it. So now with that said, we need to choose a basis, and we are told that if 1 kilomole of methane is burned, and then follows the problem statement, so which means that a simpler basis to use is actually 1 kilomole of methane. So we can just say basis. Our basis is gonna be 1 kilomole of methane, CH4. Now, if we have, remember, we are actually chasing the exhaust gas analysis, which means we're gonna make sure that any information that relates to the exhaust gas we're gonna be capturing, and the perfect place to start is actually on the reaction equation. So now, if 1 kilomole of methane is burned, we need to know how much of oxygen is going to be required to fully burn 1 kilomole of methane. So we can just say O2 theoretically required is equals to 1 kilomole multiplied by 2. So this is, this then gives us our 2 kilomole. This comes from our reaction equation that the ratio of methane and oxygen is actually 1:2. Now, with that said, if we already know how much of oxygen that is required, we can actually go further to calculate how much of oxygen was charged. Remember, the oxygen was charged as air. It wasn't just charged as pure oxygen, it was charged as air. And also the air, we are told that it wasn't just pure air or dry air, it was actually air that was 40% saturated with water vapor. So now, if we know how much of oxygen is required, especially because it is the oxygen that is going to react with the methane, then we can actually calculate how much was charged. And the information that we need to calculate how much that was charged is the fact that we are told that methane is burned fully with 10% excess air. So we can then calculate, so we can just therefore O2 charged is equals to O2 theoretically required, which is 2 kilomole multiplied by 1.1, and that gives us 2.2 kilomole. This is not the exhaust gas yet, but it's just, it just gives us the information that we're gonna need as we're going to continue doing an exhaust gas analysis. At least by now we know that how much of oxygen was charged, and because we are told that the methane burns fully, then we already know how much of oxygen did react, and that is going to be the oxygen that is theoretically required. So we have the information that 2.2 kilomole was charged and 2 kilomole reacted. So automatically it gives us an idea that then 0.2 kilomole of oxygen did remain. But then then let's keep continuing. Now as we go further, one thing that we need to understand is that, remember that now we have the amount of oxygen in the air, right? And we can actually calculate the amount of air using the amount of oxygen that was charged. And this is because that we know conventionally or traditionally that air contains 21% oxygen and 79% nitrogen. So which means if we know how much of oxygen was charged in the air, then we can actually calculate how much of dry air was charged. It's also important to understand that the air that we're going to be calculating here is actually the air irrespective of the 40% saturation of the water vapor. So with that said, we can just say let X be the total kilomole, so the total kilomole dry air charged. This doesn't really mean that the air is dry. It just means that we are actually focusing on the air, excluding the water vapor that is there, that we are told that is actually 40%. The air is 40% saturated with it. So when we say let X be the total kilomole dry air charged, we can just say therefore 0.21x, right, is equals to 2.2 kilomole, right? Yeah. So for those who might have forgotten, let me just write it here that we know that air is 21% O2, right? So we say therefore X is equals to 10.476 kilomole. Now we already have established that the dry air or the air excluding the water vapor is actually 10.476, right? Now if we know that dry air, or rather the air, is 21% oxygen, and we also know that that air excluding the water vapor it's actually 79% nitrogen, which means we can actually then use the same total to calculate the amount of nitrogen charged in the air. We can just say N2, let me say N2 charged, excuse my handwriting, N2 charged is equals to 0.79 multiplied by 10.476 kilomole, right? Let me just write here that air is equals to 79% nitrogen. Now that means this then equals to 8.276 kilomole. So now we were able to find out how much of oxygen was in the air and how much of the nitrogen was in the air, right? And as a result, we know how much of total air that was charged when we exclude the water vapor that was charged along with the air. So with that said, now when we have this information, then we can actually, just write down or go back to the exhaust gas and start to try to analyze the exhaust gas and see if we can actually get all the information we have. So we're just gonna be saying, I just want to write here that exhaust gas analysis, exhaust gas so it's actually, I just wrote there that the exhaust gas analysis, we know now we're going to find out the, write down all the information we know about the exhaust gas by now. So we know that firstly we can actually start with the oxygen. We know that O2 in the exhaust gas, okay, in the exhaust gas, O2 is equals to, remember the O2 that was charged is actually 2.2 kilomole, but the O2 that reacted is 2 kilomole. So then that will just say, you can just say it's 2.2 kilomole minus 2 kilomole is equals to 0.2 kilomole. Now we already have established that in the exhaust gas we're gonna be having 0.2 kilomole of oxygen because 2.2 was charged and 2 reacted. And also it's important to check out, is there any other oxygen elsewhere that can actually appear in this reaction? Definitely not. So which means all the oxygen that is going to be in the exhaust gas is the oxygen that remained after 2 kilomole of the 2.2 kilomole did react. So now we have established that there's 0.2 kilomole of oxygen in the exhaust gas. We then go to nitrogen. So one thing we know about nitrogen is that there's no other, the only nitrogen that came in as air, and we already calculated how much was nitrogen in the air, and there's no other nitrogen in the reaction. And another important thing is that nitrogen is inert in this case, so it doesn't react. So all of the nitrogen that came in as air actually left the combustion chamber as nitrogen, or rather in the exhaust gas. So we already know, a second thing we know of the exhaust gas is the fact that nitrogen is 8.276 kilomole. So we have established now that we know oxygen in the exhaust gas, we also know nitrogen in the exhaust gas. Now we can also go back to the reaction and say, what else do we have in the exhaust gas? When methane, all of the methane reacts with 2.2 kilomole of oxygen, it forms carbon dioxide. So the question is, how much of CO2? We know the ratio of methane and CO2 is actually 1:1, which tells us that in the exhaust gas, there's 1 kilomole of methane, of rather carbon dioxide, because methane is 1 kilomole. So with that said, we can just say CO2 is equals to 1 kilomole. So we have established also that we've also then found oxygen, nitrogen, and CO2. The next thing we need to also check out is look at the reaction again. What else forms in the reaction? Excuse me as you see my hand there. The camera seems to be blurry a little bit, so I always try to wake it up. I hope that doesn't disrupt you guys. So now we see that in the reaction also water forms, right? And the ratio of water in methane is 1:2, which means if 1 kilomole of methane reacts, then 2 kilomole of H2O is going to form. So I can just say that H2O is equals to 2 kilomole, right? But I need to highlight here that it's H2O from the reaction. Right? Yeah, it's important that I highlight the fact that the oxygen that the water that we see here is actually the water that came in from the reaction. Now the question is there any other water in the reaction, or rather in this process? Definitely yes. Remember, we are told that the air is actually charged with 40% saturated, or rather we are told that the air is actually 40% saturated with water vapor. This is actually where I'm gonna spend a little bit more time. but I'll try not to spend too much time. We need to first understand what does especially because this is actually the first video or the first lecture of this module in this in our channel. So what do they mean when they say the air is 40% saturated with water vapor? So I need to explain a couple of things. There's what we call vapor pressure, and there's also what we call partial pressure. So vapor pressure is actually something that you can actually find from what the steam tables. The steam tables actually do show actually sheets or information on vapor pressure of water. So what happens on the steam table is that you see here they say it's it's 40% saturated with water vapor, and the air temperature is at 30 degrees Celsius. That means also the water vapor is at 30 degrees Celsius. Now, vapor pressure means that it is the maximum pressure that water vapor, or let's say the vapor pressure of water vapor is the maximum amount of pressure that the water vapor can handle at a specific temperature. In this case, is at 30 degrees, which means at 30 degrees, water vapor has a specific pressure, and that pressure is called the vapor pressure. At 30 degrees, water vapor has a specific vapor pressure, and that vapor pressure is actually the maximum amount of pressure that water vapor can handle at 30 degrees. To explain that further, which means if that pressure is actually the maximum pressure that the water vapor can handle at 30 degrees, if you push the pressure of the water vapor at 30 degrees beyond the vapor pressure, then that water vapor condenses part of the water vapor into water so that it can go down to the vapor pressure. I hope that's a little bit clearer, and I believe that with time and a lot of with practice, it's gonna come more natural. So let me just write it here. It's usually denoted with P with a star and written that H2O, right? And also 30 degrees Celsius. So this you get from the steam tables, right? So the vapor pressure of water at 30 degrees is equals to 4.246 kilopascals. So that means that at 30 degrees, water vapor can handle a maximum of 4.246 kilopascals. Meaning that if you increase the pressure of water vapor at 30 degrees without but keep the temperature constant, then that water vapor would actually decrease part of the water to make sure that it remains at 4.246 kilopascals. I hope that is clearer. Now, with that said, remember our question here is we have a problem statement here. We have solved everything. Now we are left with knowing the amount or the kilomole of the water that came in as water vapor, right? We already know that there was water that came out of the reaction, but there was another water that came in as water vapor in the air according to the problem statement. So an important thing or an important approach to go about this is to say generally, or let me just write down, generally, to calculate the number of moles of a vapor or a gas, you would say in ideal situations you would say N is equals to PV over RT, right? So if this theory here, or this illustration here was actually in an enclosed container that had volume, and with this information, it was going to be easy for us to calculate the number of moles, because the pressure we have, the volume we can have, the volume we would have had, the constant, and the temperature we have. However, the challenge now is that we don't have volume here, right? This is actually a flowing system, so we don't have volume. The question is, how do we get the number of moles of this water vapor out of this whole system? So the approach that we're going to be using to actually find the amount of the water that came in as water vapor in the air is actually through analyzing all the partial pressures. So remember that we know that the vapor pressure of water vapor at 30 degrees Celsius is equals to 4.246 kilopascals. So the vapor pressure of H2O at 30 degrees Celsius is actually 4.246 kilopascals. Now we are told from the problem statement that the air is 40% saturated with water vapor. What that basically means is that the partial pressure of the water vapor that is in the air is actually 40% of the vapor pressure of water at 30 degrees. So knowing that at 30 degrees the partial pressure of water vapor is 4.246 kilopascals, that means that the partial pressure of the water vapor in this air is actually 40% this amount, because they say it's 40% saturated with water vapor. So as a result, we can just say the partial pressure of H2O is then equals to 0.4 multiplied by 246 kilopascals. And if you use your calculator, it gives you 1.7 kilopascals. So since we don't really have enough of the number of moles of everything as far as the air is concerned, especially because we don't have the number of moles of the water vapor, we're going to be using the partial pressures, because the partial, in ideal circumstances, for example, the pressure, how do I call it, like the pressure fraction is equal to the molar fraction. I hope that is clear. So in ideal conditions, the pressure fraction is equal to the molar fractions. That basic, okay, let me just write it down here just for explanation purposes. Let me write it on the side. Let me say partial pressure of any compound, let me call this compound X, right, all over the total pressure the partial pressure of any compound X over the total pressure is actually equals to the number of moles of also compound X all over the total number of moles. I hope this makes sense. That's why I said the pressure fraction is equals to the molar fraction. This is actually in ideal situations. So with that said, then we can, since we don't really have enough of the moles, especially as far as relating to the water vapor is concerned, we can use the pressure, the partial pressures, especially because we have more than enough information as far as the partial pressures are concerned. So now we have the partial pressure of water. We know that it's 1.7 kilopascals because we took this from the vapor pressure of water at 30 degrees. And then now another thing that we can calculate is that, remember, the air has actually oxygen and also nitrogen in it. So we already know that the atmospheric pressure, let me bring it here. We are told that the atmospheric pressure is actually 90 kilopascals. This 90 kilopascals is actually the total pressure of the whole air, the wet air, which means all the dry air, which is oxygen and nitrogen, including the water vapor. So this 90 kilopascals includes everything as far as the air is concerned when it's mixed with the water vapor, right? So with that said, if we know that the partial pressure of H2O is actually 1.7 kilopascals, then we can just do some simple arithmetics and get to see. My camera seems to bother me, guys, so that's why you see my hand quite often. I hope it doesn't disrupt you, but I think it's better now. So with that said, now I was saying before I got disrupted, I was saying that now that we know the partial pressure of H2O is actually 1.7 kilopascals inside the air, right? And we know the total pressure of the whole air is actually 90 kilopascals. That means that we can say the partial pressure of dry air dry air, right, is equals to the total pressure minus the partial pressure of H2O. This is to say, if everything here, the total pressure is 90 kilopascals, and we know that the water vapor partial pressure is actually 1.9 kilopascals, that we calculated it through the vapor pressure, then the remainder of the pressure is actually the pressure of the dry air, and we know the dry air is actually O2 and N2, right? So with that said, we can just say it's equals to, we know the total pressure is 90 kilopascals minus the partial pressure of water is 1.7 kilopascals, right? And if you use your calculator, that will give you 88.3 kilopascals, right? So now we have 88.3 kilopascals. And now moving forward, now that we have the pressure of the dry air, which is the pressure of both the O2 and the N2 combined, what we need to do now is actually to get the individual partial pressures of O2 and also of N2. So we can say, therefore, the partial pressure of O2 is equals to, the concept of partial pressure, like I said, relates in ideal conditions, it relates very closely with the concept of moles, right? So with that said, we know that the air composition is actually, the air composes of 21% oxygen and 79% nitrogen. So that is actually the number of moles, right, of air and of that is the number of moles of oxygen and of nitrogen. But that fraction or that ratio still exists as far as the partial pressures are concerned, which means we can say if the total pressure of dry air is 88.3 kilopascals, then the partial pressure of O2 is going to be 21% of this, which means it's going to be 0.21 multiplied by 88.3 kilopascals. And if you use your calculator, it's going to give you 18.543 kilopascals. Yeah, right? And now doing the same thing, you see the partial pressure of N2, we know that the partial pressure of N2 is going to be 79% of this, so it's going to be 0.79 multiplied by 88.3 kilopascals. And if you use your calculator, it gives you 69.757 kilopascals, right? So yeah, now that we have all this here, we can actually, find a way of so when we have reached this step, we can use either O2 or N2, or actually we should use O2. We can use N2, but it's gonna take a little bit more time. We can use O2 because we already have more solid information on it. So we can actually then use O2 to calculate the total amount of moles, and this is because the pressure fraction of oxygen is equal to the mole fraction of oxygen, right? So we don't really have the mole fraction of oxygen, but we can actually calculate the pressure fraction of oxygen and use it as a mole fraction of oxygen along with the total amount of oxygen that we calculate that was charged, and then to be able to calculate the total amount of the wet air, right? So, and from there it's gonna make it easy for us to be able to get the water vapor. So with that said, let me just take the longer route and explain, write it here and say pressure is, pressure fraction. The pressure fraction of O2 is equals to the mole fraction of O2, and is equals to, we don't have the mole fraction, right? But we have the pressure fraction, but we know in ideal conditions, these two are the same. So we can simply just then use the pressure fraction. We know the pressure fraction, we know that the partial pressure of oxygen we calculated to be 0.543 kilopascals, right, all over. Now, it's the partial pressure of oxygen all over the total pressure, and we know the total pressure of the wet air, which means is the air including the water vapor, is actually 90 kilopascals, right? And if you use your calculator, it gives you 0.206. This is actually the pressure fraction, but we're gonna take this and use it as a mole fraction because we know that they are actually the same. And this is going to help us to calculate the total amount of wet air, right? Now, for us to get there, what we're going to be doing, we can just say, let y be the total kilomole of wet air charged, right? This is all the air including the water vapor. So we're going to define y as the total. Actually, y is going to be all this air that has been charged. Why are we going that route? Because now we have the mole fraction. It's actually pressure fraction, but we're going to use it as a mole fraction because they're actually the same. If you have the pressure fraction, you have the mole fraction in ideal conditions. So now with that said, we can say, okay, if y is the total kilomole of wet air, and we know the mole fraction of oxygen inside like this wet air, then we can easily say, therefore, 0.206y is equals to 2.2 kilomole, right? This is because already back then in the first part we actually established that O2 that was charged is 2.2 kilomole, right? And if we know that is 2.2 kilomole, and we know also the mole fraction of oxygen in this whole thing, then we can easily be able to calculate the whole thing. This is actually CIR 113 and the latter part of CIR 113 and a huge portion of CIR 123. So we can say therefore y is equals to 10.680 kilomole. So you see now we're able to calculate how much of wet air, which means oxygen, nitrogen, and water vapor, charged all at the same time. We have established that that is 10.680 kilomole. Now, if we have that, then what we can actually do, we can use this same concept of partial pressure. So now we have two important things. We have the partial pressure of water vapor in this wet air, right? And then we also have, and because we have the partial pressure of water vapor in this wet air, we can be able to get the pressure fraction, and that pressure fraction, we're going to use it as the mole fraction. And after we get the mole fraction of this water vapor, then we almost are done, because remember, we have the total kilomoles of the whole of the wet air. So which means we have the total here, and then we just need the fraction. We have the total kilomole of the whole system. Now we just need the fraction, the fraction of, how do I call it? The fraction of my mind is tired, guys. We need the pressure, we need the pressure fraction to use as a molar fraction. I hope that's much clearer. This is because I need to explain this. This is because we now have established, we now have the total number of kilomole. The question we have now is, out of this 10.680 kilomole of this wet air, which means the oxygen, nitrogen, and also the water vapor, how much of water vapor is there? Now, how can we get that when we have this total kilomole? We need the mole fraction, because when we have the mole fraction, we simply multiply by this. This is another CIR 123 word, right? So with that said, because we don't have a direct mole fraction, we can use the pressure fraction, and that is actually equals to the mole fraction, isn't it? So we can say, therefore, we know that the number of moles of H2O in with air, right, is equals to the pressure fraction, I just want to write it in full here so it's easy to follow, is equals to the pressure fraction of H2O, the pressure fraction of, or let me say of water vapor, the pressure fraction of water vapor, right, multiplied by total kilomole wet air. I hope that is actually easy to follow. So the pressure, the number of moles in the air is actually the pressure fraction of the water vapor, which we go into, which is actually the same as the number or the molar fraction multiplied by the total kilomole of wet air. Now, the pressure fraction is actually the partial pressure over the total pressure. So we know the partial pressure is 1.7 kilopascals. That is the partial pressure of the water we calculated back then. And then now we know the total pressure of the wet air is actually 90 kilopascals, right? And then this is actually the pressure fraction of the water vapor. Then we multiplied by the total kilomole of wet air. And the total kilomole of wet air, we have established that it's actually we have calculated that it's actually 10.680 kilomole. Now, if you use your calculator, that is going to give you 0.201 kilomole. So, going back to the exhaust gas analysis, let me just bring back the information that we calculated. Remember, we're able to calculate our oxygen in the exhaust gas, our nitrogen, our carbon dioxide. Now, when we came to the water, we actually calculated the water that actually came from this reaction here, right? This is actually the reaction, the water that formed as a result of 1 kilomole of methane, which we have already calculated that it's actually 2 kilomole of water, right? And we have written it here. Now there's another water, so which means there's another water that we're calculating or finding a way of calculating it all this time, and we have established or just calculated that actually that amount of water it's actually 0.201 kilomole. Now with that said, that means in the exhaust gas total H2O is equals to let me see, water from reaction, right, plus water in with air, right? So that is actually the water that came from the reaction, and then also plus the water that came in with the air as water vapor, and that is equals to the water in with the water from the reaction is 2 kilomole, so that is 2 kilomole plus the water that came in with air. We just calculated that is 0.201 kilomole, so that is equals to 0.201 kilomole. And if you use your calculator, that gives you 2.201 kilomole. So we have actually answered the first part of the question. That actually was saying that actually says that they say that 1 kilomole of methane is burned, the exhaust gas will be 2.2, or they say show by calculation that if 1 kilomole of methane is burned, the exhaust gas will be 2.2 kilomole H2O, 1 kilomole CO2, 0.2 kilomole O2, and 8.28 kilomole N2. So that was actually the first part of this question here. There's another part that I'm gonna be doing now, but now we have answered this. We have proved all the information that, or all the answers that we got, we're able to prove that this is actually the exhaust gas analysis. Now, the other part of the question says that calculate the dew point of the exhaust gas. For us to get that, we actually need to calculate the partial pressure of water vapor in the flue gas. It's important that I highlight that dew point also sometimes has to do with the temperature, but in this case, we don't have enough information to actually handle the temperature part of the dew point. So we're going to be calculating the partial pressure of water vapor in the flue gas. And for us to calculate the partial pressure of the water vapor in the flue gas, we need two things. We need the pressure fraction of water vapor in the flue gas, and we also need the total pressure of the flue gas. If we have those two, we can simply multiply the pressure fraction of water vapor in the flue gas and multiply it with the total pressure, and then we'll find the partial pressure of water vapor in the flue gas. However, it's not so easy for us to find the partial pressure at this moment, but there's a concept I explained earlier right in this video, if you started in the beginning, where I explained that the mole fraction and the pressure fraction is actually the same under ideal conditions, which means if you want the pressure fraction, we actually can just calculate the mole fraction and then use the mole fraction as the pressure fraction, because in ideal conditions they are basically the same. So firstly, we need to calculate the mole fraction of H2O in the flue gas, and that would be our pressure fraction. So let's just say the total kilomole flue gas. If you remember properly, let's say the total kilomole of flue gas, we had our oxygen was 0.2 kilomole and our nitrogen was 8.276 kilomole, and our carbon dioxide, our CO2 was 1 kilomole, and our H2O, the total, we had 2 parts of H2O, and the total H2O was 2.201 kilomole. Now the total flue gas was actually 11.677 kilomole. So this is basically the total kilomole of the flue gas. So now if we know the total kilomole of the flue gas, and we also know the total kilomole of H2O in the flue gas, then we can be able to find the mole fraction of H2O. And with that said, we can just say, let me write it in full and say pressure fraction of H2O is equals to the mole fraction of H2O, and is equals to the pressure fraction of H2O is equal to the mole fraction of H2O, and is equals to the total kilomole of H2O over the total kilomole of the flue gas. So that gives us 2.201 kilomole all over 11.677 kilomole. And if you use your calculator, that will give you 0.18850. So now this is the mole fraction of H2O in the flue gas, and we know, as I've already explained, that mole fraction of H2O is the same as the pressure fraction of H2O under ideal conditions. And the question we're handling here, it's actually under ideal conditions. Now with that said, if we have the mole fraction and we know the total pressure, because remember the total pressure is actually atmospheric pressure, and atmospheric pressure doesn't change, especially because this is actually an open system. So atmospheric pressure doesn't change. It was 90 then, and it's still 90 now. So we can simply say the partial pressure of H2O in the flue gas, the partial pressure of H2O in the flue gas is equals to 0.18850, which is the pressure fraction of H2O, or the mole fraction of H2O, multiplied by the total pressure of the flue gas, which is 90 kilopascals. And if you use your calculator, that gives you 16.965 kilopascals. So now this here is basically the partial pressure of H2O in the flue gas, and that is actually the dew point of the flue gas. So thank you guys for your time, and I hope we meet again in our next video.